Have you ever boiled milk and wondered how long it would take to reach a particular temperature? Not just how fast it's heating, but how much change occurs over time? That kind of time-based analysis is exactly what integrated rate equations help us do, but in chemistry. While differential rate laws tell us how fast a reaction is proceeding at any instant, integrated rate laws go one step further. They help us predict how much reactant remains or product forms over a specific time period. These equations are derived by integrating the basic rate laws and give us a direct relationship between concentration and time. They're essential when we work with experimental data, especially when tracking reactions over several minutes or hours. And since different reactions behave differently, we use specific forms of integrated equations depending on whether a reaction is zero order, first order, or second order. You'll often see these used in labs, pharmaceutical studies, or even food science to estimate shelf life and degradation timelines. Let's start decoding them one by one.
Let's begin with the zero-order reaction, the simplest of them all. In a zero-order reaction, the rate remains constant. It doesn't depend on how much reactant is present. Yes, that might sound strange at first, but it happens in reactions like the photochemical decomposition of high hydrogen iodide under intense light. For such reactions, the integrated form is R equals R naught minus K multiplied by T, where R is the concentration at time T, R naught is the initial concentration, and K is the rate constant. When we plot R versus time, we get a straight line, a linear decrease with slope equal to negative K. The unit of K in a zero-order reaction is moles per liter per second or moles per liter per second. And it is independent of the concentration of the reactant. An example of a zero-order reaction is the photochemical decomposition of hydrogen iodide under high light intensity. Now we move to one of the most common types, the first-order reaction. In this case, the rate is directly proportional to the concentration of one reactant. As the reactant decreases, so does the rate. The integrated equation for a first-order reaction is natural log of R naught divided by R equals K times T. Alternatively, we can write it as ln of R equals ln of R naught minus K times T. This gives us a straight line graph when we plot natural log of R versus time, with the slope being negative K. The decomposition of dinitrogen pentoxide, that's N2O5, is a classic first-order reaction. You'll see the reactant decaying exponentially, but when we transform it into a logarithmic scale, the line becomes perfectly straight, making it easier to analyze. In real-life applications, this equation is used extensively in radioactive decay, pharmacokinetics, and environmental chemistry, where concentrations drop gradually over time. Let's discuss the second-order rate equation. For second-order reactions, the rate of reaction is proportional to the square of the concentration of the reactant. Mathematically, it is written as rate equals K times R squared. The integrated form of this equation is 1 over R equals 1 over R naught plus K times T. When we plot 1 over R versus time, we get a straight line. The slope of this line is K, and the intercept is 1 over R naught. The unit of the rate constant K is liters per mole per second, which depends on the inverse of the concentration. As an example, the decomposition of hydrogen iodide, where 2 high forms H2 and I2 follows second-order kinetics with respect to high. Let's bring all three orders together visually. Think of this like comparing 3 different movie plots, each with its own pace and style. For zero order, the plot of R versus T is a straight line. The reactant drops at a constant rate, like a steady leak. For first order, the concentration decays exponentially, but the plot of natural logarithm of R versus time is linear, making it easier to analyze mathematically. And for second order, It's the plot of 1 over r versus time that's linear. These graphs are not just mathematical tricks. They're practical tools to determine the reaction order from experimental data by seeing which plot gives a straight line. On the screen now, you'll see all three graphs side by side. This comparison is your cheat sheet for identifying reaction order in real-time kinetics work. Now let's apply what we've learned through a solved example. Imagine a first-order reaction where the initial concentration is 0.5 molar and after 20 minutes, it drops to 0.125 molar. We want to find the rate constant K. We use the first-order equation ln of R0 divided by R equals K times T. Substitute the values ln of 0.5 divided by 0.125 equals K times 20. That gives us ln of 4, which is 1.386. So, K equals 1.386 divided by 20, that's 0.0693 per minute. This tells us how fast the reaction is proceeding and gives insight into half-life and future concentration calculations too. That's the power of integrated rate laws, turning experimental numbers into kinetic clarity. Let's quickly revise what we've explored about integrated rate equations. These equations help us connect concentration with time, and they vary based on the order of reaction. In zero-order reactions, the concentration drops linearly with time and rate is constant. In first-order reactions, we use logarithmic relationships to track exponential decay. In second-order reactions, the rate is tied to the square of concentration and the inverse concentration plot becomes linear. These equations are immensely helpful in fields like chemical manufacturing, environmental chemistry, pharmacology, and even forensic science, where knowing how fast a substance disappears is just as important as knowing what it is. I hope this session helped you see how chemistry gives us the tools to quantify change over time, not just describe it. Catch you in the next class with more fascinating reactions and the math that makes them predictable.